Okay, I've got 9:35 and we've got a pretty fair number here today. Welcome back after the holiday weekend. We're going to jump right in. The lab test opens up. If you're in the Tuesday lab, your lab test opens up today and closes on the 17th. If you're in tomorrow's lab, it opens up tomorrow on the 8th, closes on the 18th. And if you're on the Thursday lab, it'll open Thursday and close on the 19th. So you've got 10 days to get ready for that. Lab this week is going to be all about bones. Probably start with the skull or the axial skeleton and go from there. So, any questions on anything? Okay. Well, then I'm going to go ahead and start. And we're still in chemistry, and we will be for another couple lectures. And I'm going to assume that everybody can hear me, because I'm sure you'll tell me if I can't, if you can't. So, okay. Last week, we were talking about electrons. And we talked about mixtures. We talked about mixing gravel and sand together, and sand and water, and solutions with salt and water and sugar and water and stuff like that. And anytime you have a mixture of anything, there's no chemical change involved. If you have salt and water, you can let the water evaporate and the salt will be left behind because there hasn't been a change to the water or to the salt. The same applies to sugar. It applies to any solution. So we can let the fluid, the solvent portion of any solution evaporate, and we'll leave the solute behind because there's been no chemical change to it. And the reason, is that there's no chemical change is that the very nature of the atoms, the subatomic particles, are what control chemical change. Now, if you're just mixing material together, you're not going to have any activity of the electrons. It's the electrons that determine whether a chemical change has taken place. Now, we know that atoms have electrons. We know that atoms have protons and electrons, and nearly all atoms have neutrons, everything except hydrogen. And even then, there are isotopes of hydrogen. But it's the makeup of the electrons and the protons that determine what an atom is. Protons are matched by electrons. Neutrons get thrown in there in various combinations, and that gives the atom its properties. For example, an atom of carbon, 6 protons, atomic number 6, so it has 6 protons. It has 6 electrons, and the most common type of carbon has 6 protons. 6 protons, of course it does. 6 neutrons. And it's really the electrons that determine whether or not we're going to have a chemical change taking place. Electrons are in orbit around the nucleus. Electrons are in orbit around the nucleus. Electrons have a negative charge, which balances out the positive charge or charges in the nucleus. So electrons have a negative charge. They balance the protons. Protons and electrons are exactly the same number in a balanced atom. That's an important thing to remember. In a balanced atom or a neutral atom, you're going to have exactly the same number of protons and electrons. So if you happen to encounter the phrase a balanced atom or electrically neutral atom anywhere, that means that protons and electrons match. And we have a rule here called the rule of 8s, or the octet rule. I like rule of 8s better. Atoms, if they could desire anything, want to have their valence shell filled up. Now, the valence shell is always their outer shell. Now, hydrogen only has one shell at all, one orbital. So its only shell is its valence shell. Oxygen has two shells. It has 2 electrons in its first shell and 6 in its second one. Carbon has 2 in its first shell and 4 in its second one. The first shell of every atom can only hold 2 electrons. Doesn't have to. Hydrogen only has 1 electron in its first shell, but every other atom is going to meet this requirement. 2 electrons in its first shell. That's all it can hold. So every atom except hydrogen will have 2 electrons in its first shell. Hydrogen only has 1 electron in its first shell because it only has 1 electron. After hydrogen, everybody has at least 2 electrons altogether. Now, the rule of 8s says essentially that an atom wants to have its valence shell filled up. And the valence shell is its outer shell. Whatever the outer shell is, whether it is hydrogen with 1 electron, at 1 electron in its only shell, that's its valence shell. Carbon has 2 shells. The second shell, the one with 4 electrons in it, is its valence shell. Sodium, with 11 protons and 11 electrons, has 2 electrons in its first shell. Okay, it's supposed to do that. It has 8 electrons in its second shell. Second shell will only hold 8. It has 1 electron in its third shell. It has a third shell. Now, we said last week, and I'm sure you remember this. I just remembered it now to tell you about it again. Is there are 7 shells around atoms if it has that many electrons. Now, if it only has a handful of electrons, it's only going to have 1 shell or 2 shells or 3 shells. We're never going to see anything in healthcare that we consider with more than 3 shells. So we don't care about something with 7 shells. I mean, if you ponder the nature of the universe at night, when you can't sleep, then maybe you think about the 7 shells of the electrons occupying the big atoms. But most of us just accept the fact that there are only 3 shells. An electron has energy. It has kinetic energy because it's moving. It's moving at the speed of light. It has potential energy. That's the energy it's not using. Electrons have more potential energy further away from the nucleus than if they're in close. The further away they are from the nucleus, the less energy they have to spend to keep from getting sucked into the nucleus. So an electron that is in the second shell has much more potential energy than an electron in the first shell. An electron in the third shell has even more potential energy than the one in the second, and much more than the one in the first. Whatever is the outermost shell surrounding the nucleus is going to be called the valence shell. Now, if you're an atom and you have 2 shells, 2 orbitals, you would like to be completely stable, and you would like to have your valence shell filled up with 8 electrons. Well, the only problem with that is that the number of electrons is dictated by the number of protons. You want to have 8 electrons, but you only have 4 protons, or 6 protons, or 2 protons. So you're only going to have the number of electrons you have that you have protons, but you've got room for more. If you have, like carbon, for example, carbon has 4 electrons in its second shell. It has 6 protons. That means it has to have 6 electrons. 2 electrons in the first shell, 4 in the second shell, with room for 4 more. What if there was a way for carbon to pick up more electrons without affecting the number of protons? And that's what we get into. That's the driver behind all chemical reactions. The desire, if you will, for the atom to fill up its valence shell until the valence shell is full, whether it's hydrogen with only 2, or carbon wanting to have 8, or oxygen wanting to have 8. These atoms want to achieve complete stability by filling up their valence shell. Chemical reactions, excuse me, are driven by this need to fill up the valence shell. Now, since most atoms do not have a complete filled up valence shell, they're going to do everything they can to gain electrons or lose electrons or share electrons to complete that shell, because they want to achieve absolute stability. Now, some atoms are already stable. Here we have helium and neon, 2 of the noble gases. We call them noble gases. They're lined up on the far right-hand side of the periodic table, one on top of another. They are completely stable. We call them inert. They can't react with anything. Helium has 2 electrons. Its valence shell is the first shell, the first orbital. Remember, I'm using orbital and shell back and forth now. The helium atom doesn't react with anything else. It doesn't need to pick up an electron or kick out an electron. It's stable. It has 2 protons, 2 electrons, and there's no room for another electron to come in, even to borrow it temporarily. The same applies to neon. Neon has atomic number of 10, 10 protons, 10 electrons. It has 2 in its first shell, the first orbital. It has 8, the maximum number it can have in the second orbital. Remember, it goes 2, 8, or 2 in the first shell, 8 in the second shell, and 8 or 18 in the third shell. Those are the numbers. Now that's a rule for the way the electrons line up. 2, 8, or 18. 2, 8, and then the third shell can either be 8 or 18, depending on which atom it is. Anyway, neon is filled up. It has 8 electrons in its second shell. Atomic number is 10. It has 10 electrons altogether. It doesn't react. Neon doesn't react with carbon or hydrogen or water or anything else. It's totally inert. That's why we use it as a gas in lighting, for example. We use helium for cooling purposes. We use helium in balloons. We've all seen that. It has its overall molecular weight is less than that of atmospheric air. That's why helium floats. And anything that contains helium, if the combination of like a balloon and helium gas is still lighter than atmospheric air, it will float. You put helium in a lead box, the lead box isn't going to float. So anyway, there are only a handful of atoms that are chemically inert, where their outer shells, their valence shells, are completely filled up and there's nothing else there. They are unreactive. An atom that has an electron missing, or 2 or 3 missing from its valence shell, like carbon, which only has 4 in its outer shell, it can hold 4 more, is reactive. Most atoms are reactive because of this. Now, here we go. Here are chemically reactive elements. There's hydrogen up in the upper left. 1 electron, 1 proton. The 1 electron is in its outer shell. Its only shell, its only orbital. That's its valence shell. Hydrogen would love to have a second electron there, so it's reactive. Hydrogen is reactive. It will combine with other atoms. Carbon, atomic number 6, 2 electrons in the first orbital, 4 in the second orbital, room for 4 more. 6 protons, 6 electrons. Oxygen, down here in the lower left, atomic number of 8. 2 electrons in the first orbital, 6 in the second orbital, still room for 2 more. Atoms want to get to 8 electrons. I don't know why, but they do. Atoms want to get to 8 electrons in their outer shell or outer orbital. And then here's sodium. 2 electrons in the first orbital, 8 in the second orbital, 1 in the third orbital. Its valence shell would love to get to 8. Right now, sodium is not happy. Sodium, as we see here, is unhappy because its valence shell isn't filled up. Now, to achieve this stability, atoms will form chemical bonds with other atoms. This is totally different than mixtures. Mixtures are just the physical, closeness of different types of material. Gravel and sand, salt and water. They're physically intermixed, but there's no change to their individual properties. Here we have chemical bonds where there are changes. Now, the 3 types of chemical bonds are the ionic bonds, what we call covalent bonds. They involve the covalent shell, the covalent orbital around the atoms. And we have hydrogen bonds, very weak bond, a very tiny bond, and yet it has some amazing properties. Ionic bonds. Atoms will give up an electron, or they will physically give up an electron or physically gain an electron. And they will, when they give up an electron, they have what we call a positive charge. When they gain an electron, they have what we call a negative charge. They become ions. They're not atoms anymore, they're called ions because they are charged, either positively or negatively charged. Atoms themselves have no charge. They're balanced, they're electrically neutral. 6 protons in carbon equal 6 electrons. But an ion will give up a proton, will give up an electron or gain an electron. And we find ionic bonds occur mostly in our salts, like sodium chloride. And when they come together, when we have an ionic bond taking place and salts are formed, they don't form as a molecule, they form as a crystal. So salt, here we see sodium chloride, Na for sodium, Cl for chloride, forms a crystal that looks a lot like this. We have the large fluorine atom and the negative, there's a large fluorine atom in green and the small sodium atom in yellow, but they're no longer atoms, they're ions because they have gained or lost electrons. So ionic bonds, we find them in our salts. Now, an advantage that ionic bonds have is they can break and reform and break and reform and break and reform very easily. But they're also very weak bonds. Ionic bonds get broken in water very, very quickly. You consider you're making salt water. I don't know why you're making salt water, but you're going to make some salt water. So you take 100 grams of sodium chloride, place that in a beaker, add a liter of water to it, and lo and behold, in seconds, the sodium chloride has gone directly into solution because the water is breaking those ionic bonds. And you have sodium and you have chlorine ions floating around in solution. Can't see it because it's a solution, it's transparent. Those ionic bonds have broken. Now, as soon as the water evaporates, the salt will crystallize as the ionic bonds reform. So they're easily broken, but they're easily formed. When an ion gains an electron, and this is what happens in an ionic bond. When an ion gains an electron, it becomes negatively charged. It becomes an anion. Chlorine frequently steals an electron from sodium. Sodium has 11 protons and 11 electrons. Sodium easily gives up its 11th electron because that 11th electron is out there all by itself in the third orbital, the third shell. You know, the valence shell for sodium is number 3. So you have that one electron out there, and it's not feeling any love at all from the nucleus. So that electron's out there spinning around, and sodium says, you know, if I got rid of that 11th electron, my valence shell would be filled up, and I'd be stable, even though it'd be 11 protons and 10 electrons. So it kicks out the 11th electron, and now it has 8 electrons in its valence shell. And it is now no longer an atom of sodium, it's an ion of sodium, and it has a positive charge. It's positive because it lost an electron. When you lose an electron, you become positive. When you gain an electron, you become negative. Well, that's not all that happens. The positive sodium ion is attracted to the negative chlorine ion because the chlorine ion got the electron. You know, sodium is willing to give up the electron. Chlorine grabs it. So chlorine, with its 17 electrons and its 17 protons, now grabs an 18th electron. It's negative. It has more electrons than it does protons, but they're attracted like magnets. The positive sodium and the negative chlorine are drawn together like magnets. It's electrostatic attraction. That's what an ionic bond is. There we have, on the left, we have sodium. There is a little pink electron out in its third shell, all by itself. Sodium wants to have 8 electrons in its valence shell. Chlorine wants 8 electrons in its valence shell. So sodium kicks out the electron in its shell, in its valence shell. Sodium is now stable, at least as far as it's concerned. It has, as far as the octet rule, the rule of 8s goes, it has 8 electrons in its outer shell. Chlorine has 7 electrons in its outer shell. It wants 8. So it grabs that electron from sodium. The end result, though, is that they're no longer neutral atoms. They are a positive sodium and a negative chlorine. And they're attracted together and they form crystals. All salts are made of crystals. And all salts are held together with ionic bonds. Sodium chloride, calcium chloride, magnesium chloride, calcium carbonate, trying to think of other ones. Anything that is any type of salt is held together with an ionic bond, and they always form crystals. Now, the ones that you're going to pay attention to in the body are going to be sodium and potassium and calcium and magnesium. Chlorine, you know, for all of its presence in our bodies, does not have a major role to play as far as moving energy around or conducting electricity or balancing water levels. It's always going to be sodium and potassium, and to a lesser extent, calcium and magnesium, and even further out, a little phosphorus too. So chlorine's not a major player in our bodies. It's always sodium and potassium and calcium, if you will. So, okay. Ionic bonding, primarily in the salts, primarily forming salt crystals. If you were to look at when you take If you were to shake some sodium chloride out of a container onto a glass dish, you would see the crystals on there. Every time you apply salt to food, you're shaking crystals of salt on there. You look at them under the microscope, you can actually see the shape and the pattern of the crystals. You can't see the ions, but you can see the shape of the crystal. Now, that's a chemical bond. The properties of sodium and the properties of chlorine have changed. Sodium atoms have become ions. Chlorine atoms have become ions. They come together and form a crystal. When they're not together, they're not a crystal, but they become a crystal when they have this ionic bond. Now, so we pretty much see this in the crystals and the salts, and not to discount the role of crystals and salts at all in our bodies. We need the crystals, we need the salts. You know, our plasma is 0.9% sodium chloride. It's a salty fluid. We depend on sodium and potassium for the movement of nerve impulses in our nerves and in our muscles. So I mean, we are electrically charged, and it's the sodium and potassium that allows this to happen. So just because our ionic bonds doesn't mean they're not important. But the major player in chemical bonding are the covalent bonds. In covalent bonds, we don't steal electrons. We don't kick out electrons. We share electrons. We share electrons between atoms so that we can temporarily achieve that stability of having 8 electrons, or having our valence shell full of electrons. Let's put it that way, because hydrogen doesn't want to have 8, it only wants to have 1 more electron. But with covalent bonding, we share electrons. We fill up our valence shell. We're stable. The advantage here is that since electrons are moving at the speed of light, 186,000 miles per second, we can share between 2 atoms, or 3 atoms, or 4 atoms. We can share electrons so that at any point in time, you've got a full valence shell on atom A and atom B and atom C. We haven't added any new electrons to the individual atoms. We're just sharing them. And the sharing is so fast that we're stable for the nanosecond or the micro nanosecond that they're in place there. Just take my word for it. It's one of those things that's very difficult. It's hard. It's really hard to it's hard to visualize that. So covalent bonds occur when you share 2 or more valence shell electrons between 2 atoms. So consider water. Water is hydrogen, hydrogen, and an oxygen in the middle. So anyway, so hydrogen has 1 electron in its valence shell. So, and oxygen has 6. Oxygen wants to get 8. Hydrogen wants to have 2. Hydrogen can share its lone electron with oxygen and kick the count up to 7 in the valence shell. Another hydrogen can share its lone electron with hydrogen, kicking it up to 8. Oxygen can share its electrons with the hydrogen, so they have 2 in here. So we haven't gained any, nobody has gained any electrons. We're just sharing them around. So what it means is we can fill our valence shell up part-time. But part-time happens so rapidly, since we're traveling at the speed of light. Part-time happens so rapidly the atom is stable. So a covalent bond simply shares electrons, and more importantly, it shares its potential energy. A chemical bond, for example, of sugar, we have a gram of sugar contains something like, well, 1 gram of sugar contains 4 calories of energy. So where did that energy come from? It came from, it's the potential energy stored in all the covalent bonding taking place in the sugar molecule. The sharing of electrons, the sharing of the valence electrons provides potential energy. Just let that go for a second. Now, if you are a covalent bond, you're either a polar bond or a non-polar bond. This is a covalent bond. Here we see on the upper right-hand side of the screen, you see 2 hydrogen atoms. We know it's a hydrogen atom because it has 1 proton in the middle of it in the nucleus and 1 electron in orbit around here. Now that hydrogen atom would love to have a second electron. Each one would love to have a second electron in its valence shell out here. Little blue lines of the shell. If we form a hydrogen molecule like we have in atmospheric hydrogen, the stuff that's in the air we're breathing, this atom is sharing its electron with this atom. And the atom on the right of hydrogen is sharing its electron with the atom on the left. Now you notice the electrons are moving around both nucleuses. Well, each nucleus of the 2 atoms that are joined in this molecule, they are sharing those electrons. So the electron here orbits around both this one and this one at the same time. And so at any given nanosecond, we have 2 electrons in the outer shell. We have 2 protons in this molecule. We have 2 electrons, and they move so rapidly, they are keeping the outer shell filled at any point in time. And it satisfies the need for each of these atoms to have a full outer shell, because they're sharing the electrons. Didn't gain an electron, didn't lose an electron, didn't become positive or negatively charged. We're sharing the electrons. Same thing applies down here. If you take a hydrogen atom and an oxygen atom, hydrogen has 1 electron in its shell. We see that up here in the upper right, and it would like to have a second one. Oxygen has room for 2 electrons. Oxygen and hydrogen will combine to share electrons. Hydrogen contributes 1 electron to the oxygen. It shares it. It's in orbit around the hydrogen nucleus as well as the oxygen nucleus in its valence shell. Oxygen will share an electron with the hydrogen, and it will be in orbit both around the oxygen nucleus's valence shell and around the hydrogen valence shell. So you can see, because when you watch, if you look, the hydrogen atom comes in from the side like there, and all of a sudden we see 2 electrons spinning around the hydrogen nucleus and a 7th, the hydrogen electron spinning around the oxygen. We haven't gained anything. We're just sharing electrons. Carbon is probably the best example of something that's reactive with covalent bonds. Carbon has atomic number of 6, 6 protons, 2 electrons in its first shell, 4 in its second shell. Would like to have 4 more in its second shell. The second shell or second orbital is its valence shell. There's your carbon atom right there, right here, or over here in this animation. You can see there's the 2 electrons in the first shell and 4 in the second shell with 6 protons And I'm going to assume it's got 6 neutrons here. So the carbon atom is very reactive, meaning it is very readily available to form a chemical bond with something else. And that something else is nearly always hydrogen. We see hydrogen atoms on the left, and they're not blue, but they're hydrogen atoms because 1 proton, 1 electron, 1 proton, 1 electron, all the way down here. Each of these hydrogen atoms would love to have its valence shell filled. If it forms a covalent bond, if each one of those forms a covalent bond with carbon, the carbon atom will share its electrons in its valence shell with the electrons of the valence shells of the hydrogens. And so it will contribute an electron, and so will the hydrogen. And so now we have 2 electrons in this shell here, and 2 electrons here, and 2 electrons here, and 2 electrons here. Individually, we didn't gain any electrons. We didn't add any more electrons than we had to start with. Hydrogen had 1 proton and 1 electron. Carbon had 6 protons and 6 electrons. The individual number, the grand total of protons and electrons from the 4 hydrogen atoms and the carbon atom are exactly the same. However, we have this chemical bond that has occurred has made a dramatic change here. Hydrogen atoms, when combined with carbon atoms, form something called methane. Methane gas, molecular formula of CH4, a carbon atom and 4 hydrogen atoms. Methane has more potential energy than the carbon atom does individually, and the 4 hydrogen atoms does individually. So the methane has greater potential energy than the individual atoms that formed it. It's different. Methane is useful. Methane is what we call natural gas. If you have a gas stove, if you have a gas fireplace, if you have gas heat or a hot water heater, and it is natural gas, you're burning methane. And it has a significant amount of potential energy thanks to the valence electrons that have formed it. The valence electrons contribute potential energy. And so we can measure that potential energy. We can say, methane gas has this much energy per, I don't know, however you measure it, liters, pounds, gallons, whatever. Is it liquefied? Is it gaseous state? I don't know. The point is, though, there is more potential energy. There is more potential energy in methane gas thanks to the covalent bonding between the carbon and the hydrogens. If you tried to burn a carbon atom, you wouldn't release a lot of energy. If you tried to burn an individual hydrogen atom, you would release energy with very little energy. But put it together into methane, and you have a pretty powerful molecule that can release a lot of energy. Consider if you had 3 of those methane atoms linked together, methane molecules linked together, it would no longer be methane, it would be propane. And propane is what you use at your if you have a gas grill. Propane is what you use if you don't have gas lines going to your house, like natural gas. If you have a big tank in the backyard or behind your house, and you burn that for heat and hot water and cooking and stuff like that. Propane has even more energy than methane does, because propane has is based on a 3-carbon molecule with not 4 hydrogen atoms, but with 8 hydrogen atoms. So there's a lot more potential energy because there's a lot more electrons to play with. So covalent bonds form when atoms want to become stable and they share their electrons. It also is a place to park extra potential energy. When covalent bonds form, we have lots of potential energy available to us in that bonding. Now, some molecules do it differently. Carbon dioxide lines up in a straight line. Let me go back one here. A methane atom, a methane molecule, has a looks very much like it does here in the illustration. It has a 4-sided structure. You have a hydrogen atom on each side of it. So it's sort of like a not quadrilateral, but it has 4 sides. Now, carbon dioxide, a little bit different. Carbon dioxide lines up in a straight line with an oxygen atom on either side of the carbon atom. Here we have equal sharing of the atoms. This is a carbon dioxide molecule is an electrically balanced atom. Lines up in a linear manner, not matter. And they're symmetrical. You can't tell one side from the other. So this is totally different looking than methane or water, because water has a sort of a triangular shape to it also. Now, polar covalent bonds occur when we can have a regular covalent bond, like we have in methane or propane. We can have a regular covalent bond in carbon dioxide. We can have a regular covalent bond, if there is such a thing, in sugar and glucose. 6 carbons, 12 hydrogens, and 6 oxygens has a sort of a hexagon shape because of the 6 hydrogens. It forms sort of like a ring in here, but it's very stable. One end of a glucose molecule looks like the other end. You can't tell which is which. But polar bonds are different. Polar bonds don't share their electrons evenly. While methane is sharing evenly and glucose is sharing evenly and carbon dioxide is sharing equally, water and any other polar molecule doesn't share equally. And the end result is that you have a molecule that is held together with a very strong covalent bond, but it also has a slight electrical charge on each end. Very slight charge. See, and the reason it does is that you usually have, in a polar bond, you usually have one atom that has lots of protons. And then you have other atoms that only have a few protons. And so the atoms with the large number of protons have a very powerful pull on all the electrons around it. Now consider a water molecule. Water is made up of oxygen and hydrogen. Oxygen has atomic number of 8. 8 protons, 8 electrons. All 8 of those protons in the oxygen are found in the nucleus. Hydrogen, the other hydrogen atom, have 1 proton and 1 electron. So now they're attracted to the oxygen to form water. They're going to share their electrons with the oxygen. Oxygen's going to share their electrons with the hydrogen so that everybody's going to have a full valence shell, temporarily, back and forth again and again and again. The only thing that occurs here is that you have all those protons in the nucleus of the oxygen atom, and they're attracting all the electrons. So altogether, in a water molecule, you've got 10 electrons. You've got 1 each from the hydrogens and 8 from the oxygen, and you're pulling that the 8 protons in the nucleus of the oxygen is pulling those electrons down towards the oxygen and away from the individual hydrogens. They're still sharing their electrons, but it's sort of an elliptical share because they spend a lot of time down towards the nucleus. Very powerful attraction to that great big nucleus. You have that little itty bitty electron with its negative charge fighting off 8 protons. First of all, they're big. They all also have a positive charge. Now, size doesn't matter. The charge does. You get 8 protons with 8 positive charges pulling on 1 electron with its 1 negative charge. So the electron is drawn towards the nucleus. It resists. It never gets sucked into the nucleus. It resists, but it forms an elliptical shaped orbit. And since all the electrons then are responding to that nucleus, the nucleus of a water molecule, the oxygen end of a water molecule, is slightly negative because the electrons are drawn out to the nucleus of the oxygen. The nucleus of the hydrogens are slightly positive because all the electrons are being pulled towards the oxygen. So we have a polar molecule with a positive and a negative end. Hydrogens are positive, are on the positive end of the water molecule, and oxygens are on the negative end. So we get unequal sharing. Polar covalent bonds. Again, water molecule. Oxygen is what we say has greater electronegativity than hydrogen does. So it pulls on its shared electrons, or it has a greater pull there, and pulls them down towards the nucleus of the oxygen atom. So we get this elliptical shaped orbit of those electrons. And they spin around the nucleus of the oxygen atom. They spin around the nucleus of the hydrogen atoms, but the orbit is skewed down towards the oxygen. So you have all these electrons that are moving down around the oxygen more frequently than they are in the hydrogens. Ends up slight negative charge at the oxygen end of the water molecule, right here. You see these electrons tend to cluster more frequently around the oxygen, but now at the speed of light. How do you describe frequently? The end result is that water molecules are slightly negative on the oxygen end and slightly positive on the hydrogen end. And that's an important point. That's a really important thing about water, is that water is polar. It's slightly negative and slightly positive. And that's going to attract water molecules to other water molecules and gives us the properties of water. So those are polar covalent bonds. Water is the best example of a polar covalent bond. And the third category are what we call hydrogen bonds, real weak bond. A hydrogen bond is the bond that occurs between a hydrogen atom and another molecule, like oxygen. When hydrogen bonds to oxygen, that's a hydrogen bond. It is almost like a magnetic attraction, the positive hydrogen and a negative oxygen end. It's a very weak bond. It breaks, it resets, it breaks, it resets. But this bond is so powerful, that's what holds water together. Water molecules stick together. When you pour water out on a tabletop, it forms a big puddle. It holds together in a puddle. It doesn't go flying off into space in the individual molecules. when you pour water into a container, it splashes up on the sides of the container and sticks there. It is the properties of water that holds it in place. Properties are whatever. Because of hydrogen bonding. Hydrogen bonding also forms the shape of large molecules. Large molecules are twisted around in their specific shape thanks to hydrogen bonding that occurs between the various molecules, various smaller molecules within the large molecule. Yeah. One of the reasons that DNA has its shape of a double helix, a circular, like a spiral staircase, if you will. It occurs because of hydrogen bonding with the various atoms in the DNA structure and causes it to twist in its unique shape. So hydrogen bonds, very weak molecule, very weak attraction, and yet at the same time, it's a very powerful attraction. Okay. Let's see if this works. Let's see if you can hear this.
The atoms that make up a water
Consider when you want to boil water. You put water in a pan, put it on the stove, turn the stove on, and then you wait. You wait until it starts to boil, until the water reaches 212 degrees Fahrenheit or 100 degrees Celsius in here. For water to boil, you've actually got to break those hydrogen bonds. So it takes a tremendous amount of energy to boil water. You know, it's all relative because we boil water all the time. But it takes a great deal of energy to break those hydrogen bonds. And every time when the water is boiling, the bonds are finally breaking. So you can boil water. You are getting those bonds to break. Now, what about freezing water? If you put water, if you use ice cube trays, for example, if you put water in ice cube trays and stick it in the fridge, in the freezer, that water will eventually form ice cubes. Now, or you have an ice maker in the door of the refrigerator, and the ice or inside the refrigerator, inside the freezer part, and it has to fill up with water to freeze. There, you have for ice to form, you have to get those hydrogen bonds to become even stronger and to stop moving, because these things move all the time. We have to slow the movement of the electrons down for ice to form. So these hydrogen bonds are very, very important to us for water. You'll notice that each water molecule can be attracted to 4 other water molecules, and those 4 can be attracted to 4 more, and pretty soon you have a whole bunch, that's a technical term, a whole bunch of water molecules linked together into a big drop of water or a puddle of water or into a container of water. It gives water its unique properties. Water sticks to each other. As I said, if you pour water out onto a surface, it's going to form a puddle. It's not going to just instantly disappear into space. One last category here called van der Waals. Van der Waals is a very, very, very transitory, very brief attraction that occurs between large molecules that are very close together. And as the electrons of each of the atoms inside the molecules move around and change position, when they're in orbit, as they temporarily become slightly more positive or slightly more negative, the very large molecules are attracted to each other. And it makes a solid. It comes together and changes the density of the substance, of the compound. So, for example, animal fat, like butter, is solid at room temperature. The long molecules that make animal fat are very close together. And as the electrons shift their positions temporarily, I mean, we're talking nanoseconds, are attracted to each other with their slightly positive and slightly negative charges, and they stop moving just for a second. They're attracted like magnets. And then they break apart and do it again, and do it again, and do it again. What that attraction is, van der Waals attraction, is what gives animal fat its property of being solid at room temperature. Because the fat molecules are long chains that are very, very close together to each other in the substance, in the butter fat. Liquid fats, oils, the long chains of molecules are further apart. There is no van der Waals attraction, so they stay liquid at room temperature. Animal fats are solid at room temperature. Plant fats are liquid at room temperature. Animal fats have this van der Waals attraction. It's about the only place we see it. Whether you have a butter on the table or you're trimming the fat off of a piece of meat, for example, it's solid because of the van der Waals attraction. So anyway. So now we know why chemical reactions are important to us. Let's talk a little bit about them. So remember, our bodies are full of chemical reactions taking place all the time. That's what metabolism is. Our metabolism is simply the sum of all chemical reactions taking place together. Chemical bonds are going to happen when we break bonds, when we make bonds, when we rearrange the bonds. If we are boiling water, we are breaking bonds. If we're freezing water, we are making bonds. If we are if we're eating something and we're breaking down sugars to release energy, we are breaking covalent bonds. When we eat carbohydrates and we store it in our liver as glycogen, we are making bonds. Now, every chemical reaction is always going to have a reactant and a product. The reactants are the substances that come together to form, reactants cause a reaction. It's sort of that's pretty redundant there, but it's basically the truth. The reactants are what you bring together to cause the event, the chemical reaction to occur. If you mix together baking soda and vinegar, and who hasn't done that somewhere along the lines, who hasn't done a middle school volcano science fair project with baking soda and vinegar? You know what happens? It bubbles and foams and the volcano erupts, it's just like, I used to judge science fairs. I can't tell you how many volcanoes I've seen. But we all play, at some point growing up, we all played with baking soda and vinegar. Baking soda, sodium bicarbonate, and vinegar, mostly acetic acid. Acetic acid is an acid. Sodium bicarbonate is a base. When you mix a base and an acid together, there will be a reaction. Baking soda and vinegar gives you that reaction. You have the release of energy, you have the release of carbon dioxide. The reactants were baking soda and vinegar, acetic acid and sodium bicarbonate. The products are a release of energy, a release of carbon dioxide, and water. The end result of your volcano was always the bubbling, thanks to the release of carbon dioxide and water. So the reactants are what cause the reaction to occur. The products are what's left over at the end. And believe it or not, reactants and products tend to stay balanced. What you started with is going to be what you end up with if you factor in the amount of CO2 given off in our volcano. You take into account the amount of carbon dioxide coming off, the energy released, and the water left behind. So reactants and products. Our bodies are having reactions with taking place all the time. We have reactants and we have products. We break down glucose from the foods that we eat. You know, glucose the sugar is a reactant. The product is carbon that's given off is energy plus carbon dioxide plus water. That's what happens when we break down food. The end result is a release of energy and carbon dioxide and water. We usually write chemical reactions using the molecular formulas of the individual molecules. For example, glucose, C6H12O6. You'll be tired of hearing that. Hopefully you won't be saying it in your sleep, but C6H12O6 is glucose. Glucose is the carbohydrate that our bodies use for energy. We break down, we oxidize glucose in our bodies, in our cells, and release the energy. Where's that energy coming from? It's coming from it's the potential energy held in the valence electrons of the glucose molecule. Glucose, 6 carbons, 12 hydrogens, 6 oxygens. It has a lot of stored energy in there. A molecule of glucose stores about 680 kilocalories of energy, which doesn't mean anything to us right now, but it will. That's a lot of energy in one molecule. We can take some of it, we get to use about 40% of that energy. About 260 kilocalories we get to play with and do things with. The other 60% goes off as body heat. But we can take a molecule of glucose, get 40% of its stored energy and do things. When we write C6H12O6, we're describing a molecule of glucose. That is its molecular formula. Or H2O, that's its molecular formula. So we're describing a molecule, and we can, if we know how much energy is available there, we can say, well, molecule of glucose, 680 kilocalories of energy right there. That energy is what we see in food labeling. When you eat a Nutri-Grain bar and it says 140 calories, if we eat an apple and we look up and it says 60 calories. If we go by Burger King, and Burger King now has their big menus out, where you're ordering, well, like they always have, but now they're showing the calorie content too. And again, one of the very large, I don't know, it's like the Whopper, the King Whopper, or whatever they call it, somewhere around 1,200 calories of stored energy in there. I'm not taking any position on that. That's just, and again, calories aren't evil. Calories are just a measure of the stored energy. That's all it is. Calories themselves are not anything. There's nothing wrong with a calorie. It just just a measure of the energy stored in that particular item. You know, we can measure the calories in a log, see how much energy is going to get released when the log burns, or in gasoline or in diesel. It's simply the amount of stored energy, and every molecule has a certain amount of energy, of potential energy in its valence shells, some more than others. In anatomy, in our bodies, we have 3 types of chemical reactions that take place. A synthesis reaction, where we take little things and make it into something bigger. Little molecules make a big molecule. So if we eat carbohydrates, maybe you had a bowl of cereal this morning, or you had an apple, apple's full of starch, or you had a baked potato yesterday, or fries, or something, doesn't matter. The carbohydrates that you ate are broken down to glucose, a simple sugar, C6H12O6, and enter your cells. Insulin allows your cells to take in that sugar. The cells will take in all they possibly can hold, and any leftover sugars are sent to the liver, where they're recombined to form a compound known as glycogen. Glycogen is the human version of starch. It's a what we call a polysaccharide. It's a great big sugar molecule, great big carbohydrate molecule. So we take little molecules of glucose and we make big molecules of glycogen. We store in there. We store excess sugar in our liver as glycogen. Or we take protein, and you break down the protein into its individual components. Protein is made of something called amino acids. The individual amino acids can be reused in our bodies to make other proteins. So we eat a cheeseburger, and the protein that's in the meat is broken down to amino acids and then reassembled into a new protein for us. Anabolic reactions take little molecules and turn them into big molecules. And it always takes energy to do this. Anabolic reactions require energy. We convert small molecules into big ones. Consider baking a cake. If you mix all the ingredients together, the oil and the water and the sugar and the flour and the flavorings and whatever it goes into a cake, eggs, milk, I don't know. You mix all that together and let it sit there, you're not going to have a cake. You need to have some sort of synthesis reaction to take place. So what do? You take all that mixture, the cake batter, place it in the oven, turn the oven on. That's an important point. Turn the oven on, and in 30 minutes, you don't have a pan full of batter, you have a cake. Totally different than what you started with. The oil and the water and the flour and the sugar, those were all combined in the batter. That was just a mixture. It was a physical mixing of those properties. But when you place it in the oven, they rearranged themselves into larger molecules. You applied energy to the batter and it turned into a cake. It changed. It can't go back to being batter. It can only stay as a cake until you eat it. Synthesis reactions are building reactions. A plus B yields AB. Decomposition reactions are just the opposite. We break things down to their simplest form. And this is a catabolic reaction. Anabolic reactions build things up. Catabolic reactions tear things down. With catabolic reactions, we break bonds and release energy. So you bake the cake. Now you eat it. And you convert that cake back into glucose. And you're releasing the energy stored in the sugar molecules in that cake, in the carbohydrates in that cake. Yeah, so you break the bond, or you eat you had a cheeseburger again. The protein in the meat is broken apart into its amino acids. It still releases energy. The amino acids are then reassembled. So we go from a catabolic reaction back to an anabolic reaction. We've changed it. The protein that's in your muscles or in your collagen fibers that give great strength to your bones, for example, that protein may have been the cheeseburger or the vegetable protein that you ate 2 days ago or a week ago or this morning. Yeah. Protein is all the same. There's only 20 amino acids that make up proteins. Where we get, whether it comes from plants or animals, doesn't matter. More on that later on. But all the amino acids are going to be the same amino acids in whatever source we get. Catabolic reactions break large molecules down into small ones and release energy. Anabolic reactions take little molecules with energy and make big molecules. And the third category are the exchange reactions, where you're going from a large molecule to a small one, back to a large molecule, or the other way around. Yeah, so when you are eating something, you eat that cake that you baked. Well, the baking the cake was an anabolic reaction. Now you eat the cake and break it apart. That's a catabolic reaction because you're releasing energy. But the little molecule, the leftover molecules of sugar that you couldn't process because of your cells are full, end up being reassembled into a large molecule, again stored in your liver. So that is an exchange reaction, because you have both synthesis and decomposition. Exchange reactions have both anabolic and catabolic parts. Exchange reactions in human systems are called oxidation reduction reactions, or redox. This is chemist talk now. Reduction, oxidation, oxidation reduction, redox. It's all the same thing. We say an atom gets reduced when it has gained electrons. It's oxidized when they lose electrons. So every time you light a match or light a lighter or light a candle, that is an oxidation reduction reaction. The wax in the candle is being oxidized. It is being burned. You're using the wick to hold the flame next to the paraffin of the candle. The candle wax is breaking down. It's releasing its stored energy. It's giving off electrons. Every time something is burning, it releases electrons. And when it releases electrons, it releases energy. That's why there's light and heat coming off of a candle. Light and heat are occurring when the electrons are being let go from the burning candle, so that you're oxidizing the candle. You're oxidizing the wax. Same thing happens in our bodies when we break down carbohydrates. We are oxidizing the carbohydrates. We are releasing electrons. Now, in our case, we are releasing energy. Some of it comes off as heat, other comes off as chemical energy that allows us to do things. Now, what about reduction? Well, reduction is a term that chemists use to describe the gaining of electrons. Only chemists would say reduction when they're talking about a gain. But those electrons that are being given off, when you're breaking apart the cake or burning the candle, or you're throwing charcoal on a grill or burning a log in the fire pit. That's oxidation. It's releasing energy. It's releasing electrons. Those electrons are being released. It's giving off the energy. Where are those electrons going? The universe has to stay balanced. All those electrons have to go somewhere and be captured by something else. Those electrons have to go somewhere else, and they have to be captured. And something that whatever's capturing those electrons, we say is reduced, because when it grabs electrons, it has even less positive charges than it did before. When we are releasing energy, the electrons go somewhere else. We'll talk a lot about that when we get into metabolism. Another term here, and go along with catabolic and anabolic. Reactions can either be exergonic, where they give off energy, catabolic reactions, breaking down large and small into small, are exergonic. Oxidation reactions, burning a log in your fire pit, breaking down food in your body. Those are catabolic or oxidative reactions. We are giving off energy and breaking down large molecules into small ones. Endergonic reactions require energy. The product of an endergonic reaction has more potential energy than we started with. When you bake a cake, there are more calories in the finished product of the cake than you started with all the ingredients, as a mixture. When you have the chemical reaction taking place that forms the cake itself, we have more potential energy stored in there than we started with. These are anabolic reactions. Where did that potential energy come from? Where did the potential energy come from? We applied energy from the oven. It allowed the chemical reaction to occur, and we parked a lot of that energy into the molecules there. Now, chemical reactions are supposed to be reversible. In a lab setting, a chemist can reverse a reaction. In our bodies, it doesn't work that way, because when we have a chemical reaction, we have a catabolic reaction. When we break down the reactants, the products are usually carbon dioxide and water and the release of energy. So we can't go backwards. We can't reverse that reaction. That and the fact that the reactants in our bodies, the concentrations are so small that the concentrations are so small to begin with, and after we break them down and release carbon dioxide and water and energy, there's nothing left to go back. So it's almost impossible for us to reverse chemical reactions in our bodies, and that's okay. The end result of a chemical reaction in our bodies is the release of energy. On one side, it's release of energy, release of carbon dioxide, and release of water. Or the end result of a chemical reaction is to take little molecules and make big ones. We can't go backwards in our bodies. And we have very little control on the rate of chemical reactions in our bodies. Chemical reactions are affected by temperature. Things go faster at higher temperatures. If you're going to bake your, if you're going to bake your cake in the oven, are you going to put it on 250 or 350, which is going to get done faster? The higher temperature makes the reaction go faster. Higher temperature will cause an increase in the chemical reactions. Are you going to add sugar to your tea at room temperature, or are you going to add sugar while the tea is still hot, right after you made it, if you're going to make sweet tea? It's going to work better at the higher temperature. Temperature affects chemical the rate of reaction. Concentration of the reactants. If some is good, more is better. It's one of the few times it actually works. And the more reactants you have, the better the reaction is going to be. If you're showing off your baking soda and vinegar volcano at the science fair, you have lots of vinegar and lots of baking soda, and you get a nice reaction that lasts for a while. So when the judges come around, it's still going on, not, oh, well, it was working type of thing. The more reactants you have, the faster it's going to go. You know, again, if some is good, more is better. And the third thing that applies is the size of the particle. Smaller particles react faster because there's more surface area for them to meet. There's a greater chance for them to encounter other molecules because there's a lot of them. So if you have lots and lots of particles and they're all very tiny, you're going to have a good reaction. You're not going to throw, if your goal is to make iced tea, sweet tea, you're not going to throw a 10-pound block of sugar into your tea, because it's going to go in solution very slowly as it dissolves. You're going to throw in a bag of granulated little tiny grains of sugar. It's going to react very quickly. The smaller the size of the particle, the better it's going to be. However, none of these affect us in our bodies. We can't change the temperature of our bodies. Our body temperature stays constant at 98.6 or 100 degrees Celsius. We can't get people warmer to work faster. The only time that works for us is when we have a fever. A low-grade fever makes our metabolic rate go faster to help get rid of, pathogens. That's a good thing, but it's only temporary. We can't do that. We can't raise our temperature to make reactions go faster. The concentrations in our bodies are very, very tiny to begin with. So we can't affect the concentrations. And the particle sizes are very, very small. So none of these things apply to us. So the only way that we can make reactions work for us very easily, and this is the last point for today, is using something known as a catalyst. A catalyst causes a chemical reaction to go faster without affecting the reactants themselves. Catalysts enable the chemical reaction to go faster. And in our bodies, our catalysts are known as enzymes. And I'm going to leave it with that, and we'll start up with that on Thursday. So let me get out of here. Okay. So any questions on any of this? I know it's a real exciting topic to come back to after vacation, after a short vacation, but just bear with me. It'll get better. Trust me. So, okay, lab this afternoon, we'll be looking at bones. So, and the lab, today's lab, the Tuesday lab test opened up today. So, I'm going to get us out of here because I have 10:59, and I will see you all later on.